Alright, so this is all about solutions and how they are formed and calculating molarity and all that stuff. This is the first part of chapter 11? Yes. Alright, so I want you, like when you think of a solution, typically we think of a solid dissolved in a liquid that makes a liquid type solution. But that's just one type. There are many different types of solutions. And they don't all have to be solid. So looking at this chart here, it has the state of the solution right here, and then what the solute and the solvent are. To review, a solute is the substance that is dissolved. So, thing dissolved. And the solvent is the substance doing the dissolving. I'm gonna run out of room. Dissolving. Alright, so in terms of like classifying or assigning which one's the solute and which one's the solvent, it really only has to do with how much of each substance is present. The solvent will always be in a greater quantity than the solute. So, yeah, but it really doesn't matter because they're being dissolved and they're mixing together and all that stuff. So for example, air is a solution. It's a gas solution, and it's a mixture of nitrogen and oxygen and other random gases. Vodka, this is straight from the textbook. I don't know why they chose to use vodka, but vodka and antifreeze are both liquid solutions. Vodka would be a solution of water and pure ethyl alcohol and some other liquid stuff. Antifreeze, I'm not exactly sure what's in that. I believe methanol is one of the things. Brass is an example of a solid solution where you have a mixture of two different solids. If you recall, brass was copper and zinc. Carbonated water, that's a pretty common example you'll see where you have a liquid with gas dissolved in it, which consists of carbon dioxide dissolved in the liquid soda stuff, the water. Alright, seawater or a solution of sugar, that's our most stereotypical solution or our most common solution where we have a solid dissolved in liquid forming a liquid solution. And then very infrequently, doesn't happen very often, you can have a gas that's dissolved in a solid, making a solid solution. An example of this is hydrogen in platinum. The hydrogen molecules, the gas molecules, are so tiny that they actually dissolve within the platinum solids a little bit, kind of like with an alloy where it's like an interstitial one, but instead of it being another solid that's inserting itself in the gaps of the metal, it's a gas. So that's another example. So moving on, we're going to review briefly, very quickly, the different calculations. Most of this should be familiar. You should know this from last year. Molarity, the most common one, moles of solute over liters of solution. Mass or weight percent. You often see this with medicine. They, like the IVs and stuff like that will tell you it's 0.5% this or whatever. But that's like percent composition. That's just a percent where you have the mass of the solute over the mass of the solution. So the solution needs to be the solute plus solvent, and then times 100. Mole fraction we saw back with gases, and that's the moles of whatever substance you care about divided by the total moles of the solution. And then molality, you might have had to calculate this last year. It's moles of solute over kilograms of solvent. They actually just recently, within the redesign, decided to no longer require the use of calculating molality on the AP exam. But we use this with colligative properties. Colligative properties, which is the end of this unit. They still expect you to understand how colligative properties occur and how molality affects those colligative properties, but they don't actually ask you to calculate them. So we can pretty much ignore that formula, but just know it exists. All right, so let's run through some examples pretty quickly. So with this one, we have 1.00 moles of sugar in 125.0 milliliters of solution. We want to calculate the concentration in molarity. Now remember, molarity is moles per liter. So we have 1.00 moles over 0.1250 liters, which gives us a molarity of 8.00. We want 3 sig figs because our lowest number is 3 sig figs, moles per liter. All right, this next one we have 10.0 molar. We have a 10.0 molar solution of sugar. We want to know what volume of the solution do we need if we want 2 moles of sugar. So we can set this up like a formula. We know that molarity is moles per liter, and if it's 10.00 moles per liter, that's the same as 2.00 moles over what volume? So if we solve for volume, we should get 0.200 liters. Again, 3 sig figs because our givens have 3 sig figs. And then, now you could have, backing up to the problem we just did, you could have done that with stoichiometry or the way I did it, or you're solving the formula. It really doesn't matter, just as long as you get the right answer. All right. In this one, we have 2 separate solutions, one of NaOH and one of KCl. Each one of them, we dissolve 100 grams of the solute in 250 milliliters of the solution. We want to calculate the concentration of each in molarity. So I'm going to do NaOH over here first. So we first need to convert the grams to moles. And the molar mass of NaOH is 40.00 grams. So we get 2.500 moles, which we then divide by, I'm going to change colors, you divide by the volume in liters, and you should get 10.00 moles per liter. All right, with the other one, KCl, again, same thing. We need to convert the 100 grams to moles, but KCl's molar mass is 74.55. And we get 1.341 moles, which we then divide by the 0.2500 liters, and we get, running out of room, 5.364 moles per liter. All right. Do more practice with that. There's plenty of problems in the book that you can practice that, or just go back to Chem 1 and practice doing those those calculations. All right, a mass percent problem. Okay, it's percent, so it's part over whole times 100, but this time it's of mass. So mass of the solute, we want to find the percent by mass concentration of glucose in a solution made by dissolving 5.5 grams of glucose in 78.2 grams of water. So the thing being dissolved, or the solute, is the glucose, so 5.5 grams, divided by the mass of solution, which is 78.2 grams plus 5.5 grams, and then times 100. And with 2 sig figs, you should get 6.6%. Now, you can't just leave it like that. You actually have to label with what it is you're talking about. So you would say 6.6% glucose by mass. So that's really important because there are such things as percent by volume. We don't use that a lot in chemistry, but there is such a thing as percent by volume. There's also mass by volume, so you just need to be really clear with what it is you calculated. All right, mole fraction. Again, we did this back in gas laws. So we have a solution of phosphoric acid was made by dissolving 8.00 grams of H3PO4 in 100.0 milliliters of water. We want to calculate the mole fraction of H3PO4. So we need to take the 8.00 grams of H3PO4 and convert that to moles, because it's mole fraction. And then we also need to know the moles of the water because we need to find the total moles of the solution. Now, you're given that water has a density of 1.00 grams per milliliter. Now, if they tell you that in a problem, or if they say it's at 25 degrees Celsius, you can assume that that is correct. Otherwise, don't assume that water has a density of 1 gram per milliliter. You have to be told it, or you have to be told it's at 25 degrees Celsius. Otherwise, there's another way to do the problem. Okay, so here we can take the 8.00 grams of phosphoric and convert that to moles. Phosphoric acid has a molar mass of 98.00 grams per mole, and so we get 0.0816 moles of H3PO4. With water, we can assume that the 100 milliliters of water is 100 grams of water. So then we can convert that to moles. Each gram has a molar mass of each mole has a molar mass of 18.02. So we get 5.55 moles of water. So now when we find mole fraction, we're going to take the substance we care about, which is the phosphoric acid, and divide it by the total moles. This is, remember the big X, that's mole fraction, H3PO4 equals 0.0145. No units for mole fraction, but you need to make sure you label it like I did with the X, H3PO4, and the X is the Greek letter chi. All right. And, yep, can just ignore that. Just know it exists. All right, so now let's take a moment to discuss how solutions are actually formed. So here is important part. All right, so the driving force to something dissolving is this thing called entropy. Okay, you hopefully learned about entropy last year. Don't know if you did or not, but entropy is, and we're going to spend a lot more time on this when we do another chapter, but entropy is disorder. The universe doesn't like order. It likes things to be disordered. So, for example, if we were to dissolve NaCl in H2O. If we were to mix NaCl and H2O, and the NaCl just kind of stayed on top of the water and didn't actually mix with it, that's still very ordered. NaCl is a very ordered substance. H2O is a very ordered substance. The universe doesn't like it to stay as ordered. It'd rather mix things up a little bit and create some disorder. So the driving force behind solution formation and the dissolving process has to do with, is it more energetically favorable to have the substances mixed together than to have them not mixed? So, for example, in NaCl and H2O, NaCl is held together by electrostatic attraction, and H2O is held together by the IMS, the hydrogen bonding. If the energy that, by overcoming any of those forces, it requires energy, yes? If the energy required to overcome those things that hold one of themselves, like the NaCl to another NaCl, or an H2O to another H2O, if that energy is less than the energy that is released when they come together, then the substance will dissolve. So, for example, NaCl is more attracted to the H2O molecules than other NaCls. So it's going to want to form a solution. It's going to want to be dissolved. Now, other substances where they don't dissolve, that's because they'd rather be attracted to themselves than the things that you're trying to mix them with. Okay? So that goes through all that. So this is showing this is showing it with pictures, how it's happening. So, looking here, we can say that our solute, in this case, is, for example, NaCl. Okay? In order to dissolve, it's actually a 3-step process. Step 1 is you have to expand the solute. You have to overcome those forces holding them together. Well, to go from this to this, it requires energy. So that would be a positive delta H value. It takes energy to do that. Like, it's not going to be releasing energy. That requires energy to do that. Step 2, our solvent, say this is H2O. Step 2, to expand our solvent also requires energy. Now, if the energy that required to expand them ends up being less than the energy that is released when they come together, then it is an exothermic process. So here, when they come together, when they dissolve, if this delta H, this here, step 3, this is negative, typically it will be negative. There are a few cases where it won't be, but that's where it really doesn't mix. But if they want to mix, this will be negative. It releases energy because it's like, oh yeah, I'm together. I can release some energy. All right? So you take delta H1 plus delta H2 plus delta H3, and that gets delta H of our solution. This delta H solution can be negative or positive. It's negative if the solute wants to dissolve. That's exothermic. It's positive if the solute really doesn't want to dissolve, or it takes, doesn't release as much energy as it took to expand the solute and the solvent, and that'd be endothermic. All right, so this is showing, this is explaining the picture in words, kind of. So step 1 and 2 require energy, that's positive. Step 2 usually releases energy, so that's negative. Step 1 and 2, remember positive is endothermic. Step 3 is exothermic. It says often, but for our purposes, most of them will always be exothermic anyway. So, yeah. Add them all up. Whatever that sign is tells you if it's positive or negative. This tells us for our final solution. If it is endo or exo. So kind of like with our hand warmer lab. If it released more energy than it took to, break apart the things or overcome those forces, then it was exothermic. And if it didn't, then it was endothermic. Right. One more way to explain this. Now, these graphs are a little confusing at first. If it's an up arrow, like on the graph itself, if it's an up arrow, that means energy is going in. If it's a down arrow, that means energy is coming out. So looking at this first one, delta H and delta H1 and delta H2, energy is going in. So that's positive value. Delta H3, energy is going out, so that's a negative value. Since the delta H out, delta H3, is a much larger quantity than the sum of delta H1 and delta H2, the delta H of the solution is releasing energy, so this is exo. In this one, the other one, it's not exo, it's endo. The delta H in, the delta H1 and 2, the energy in, and delta H3 is our energy out. See, the energy out isn't more than the energy that we had to put in, so delta H solution is still requiring energy, so it's positive, and therefore it is endo. So when you're given a question like this, you can explain it with a graph like this, you can explain it in words, or you can explain it with pictures. It really doesn't matter. Or you could do all three, but you'd only get so much time. So pick a way that works for you. All right, so looking at this, we're going to explain why water and oil, which is a long-chain hydrocarbon, do not mix. And then it says here in your explanation, be sure to address how delta H plays a role. But since we know water and oil won't mix, delta H really isn't playing a role because they don't want to mix together. Right? So we know that water is polar and oil is nonpolar. Whenever you get a problem like this where it's asking you to compare things and saying, it might ask you, will they mix or not? Immediately identify the types of substances. Are they polar or nonpolar, or is it a mixture of them, or whatever? So, once separated, water molecules are more attracted to themselves than to oil molecules. so mixing doesn't happen. It's not energetically favorable. And then not energetically favorable talks about that. That's really what's happening with delta H. Delta H is showing that it's not energetically favorable, so it's not going to mix. Okay. And in your packet, I didn't notice this until after I copied it. This question was repeated twice, so you can just ignore the next little part. All right. So in general, one factor that favors a process is an increase in probability of the state when a solute and solvent are mixed. That is entropy. Okay? So the universe favors disorder. Okay? Processes that require large amounts of energy tend not to occur, i.e., oil and water. Mixing. Takes too much energy to do it, so it's not going to happen. There's no advantage, there's no energy advantage for it to mix, so it's not going to. Now, back in Chem 1, you learned like dissolves like. Polar substances dissolve polar substances. Nonpolar substances dissolve nonpolar substances. But if all you say, like if this was an AP question, and all you said is like dissolves like, you would not get any credit. All right? You have to explain what that means. Now you can start off your, explanation with like dissolves like. For the example, the last one, talking about how oil and water won't mix, you can say like dissolves like, and they're not the same. So you have to explain that polar substances would be more like if you had two different polar substances mixing, a polar substance would be just as attracted to another polar substance as it is to itself, so it's energetically favorable to dissolve. And the same thing with nonpolar substances, and then explain why polar and nonpolar wouldn't dissolve, because it's not energetically favorable. So don't just say like dissolves like. Your paper will not actually explode, but you will not get any credit. Okay?